Yeah, so good evening, everyone. So, I'm talk about fluid transport. So, basically, anything concerned about fluid transportation from one point to the other, whether using a siphon, whether using a pump, and even the way to measure the fluid flow. You get it. So, basically, talking about fluids, you're talking about liquids and gases, right? So, you're talking about, come to talk about them. So, starting from the mathematical review part of fluid transport, you come to talk about the vectors, right? Where we have vectors, we have scalars, we have tensors, right? By trying to group them in terms of their tensors, right? Their degrees, right? So you have the scalar being called the zero tensors, the vectors being called the first order tensors, then we have the tensors being called the third order tensors, right? Having all those components, right? So the formula we basically use is 3 raised to the power n. Alright, so if you have a scalar, meaning that for a scalar, I'm trying to talk about a zero tensor, right? So that means that we have three components. So we have one, right? So meaning that we have just one component which defines a scalar and which is the magnitude, right? But when we are trying to talk about a vector, which is 3 to the power 1, which is 3, right? So you're talking about three components that defines the vector. So if let's say you have a velocity vector, we can have the vi, so vxi plus the vyj plus the vzk. Right, so you can see that we have what three components defining the vector, right? And whereby we have the third order tensor, and sorry, the second order tensor, where we have nine. Right, so over here we have example like the shear stress, right, um, having nine components over here. So let's dive into the first question where we have if A is equal to A1I plus A2J plus A3K, and we have B being equal to B1I plus B2J plus B3K, and they've asked us to prove whether A dot B gives us A1 plus B plus A2 B2 plus A3 B3, right? So the dot product, right? So what we can do is that vector a1i plus a2j plus a3k, this one over here, right? Dot then the vector b, which I have b1i plus b2j plus the b3k. And so over here, I'll be taking the how to multiply to when you have two brackets, how to open them. So over here, I have my a1i, which will multiply b1i plus b2j plus b3k, then the a2j also multiplies the b1i plus the b2j plus b3k, then plus the a3k also multiplies the b1i plus b2j plus b3k. So over here, what you'll be having here is that the a1i times the b1i gives us a1 b1, and we know that I dot I is 1, right? I dot I is 1, j dot j is 1, then k dot k2 is 1, right? So over here, you will end up getting a1 b1, then plus we can see that we get a1 b2 multiplied by 0 because I dot j is 0, plus a1 a1b3. Then we can see that I dot k I dot k2 also gives us 0. Yeah, I dot k also gives us 0, so we also have 0. Then plus, then we move to the a2 side. So that one to have a2 b1. Then you can see that j dot I is also 0. Then plus, then we have a2 b2 j dot j is 1, right? Then we move to the last one, which is the a2 B3. Then you can see that j dot k is also 0. And move to the last one, which is A3, right? A3B1. Then you can see that k dot I is also 0. Then plus, then we have A3 B2. Then k dot j also gives us 0. Then plus A3 B3 k dot k gives us 1. Right, so here goes to 0. Here also goes. Here goes away. This one also goes away. This one goes away. This one goes away. So right now we will end up with A1 B1 plus A2 B2 plus A3 B3. Right, so right now we've ended up with the answer. So when we find the dot product of these two vectors, we've actually proved that we will be having A1 B1 plus A2 B2 plus what? The A3 what? B3. Yeah, so that's for question 1. Right, so let's try question 2. So question 2, where um we have two vectors, right? And they've asked us to calculate the angle between what? Those two vectors, right? So what we'll be using is the dot product over here. So we have A dot B will give us AB cos theta, right? So the A and B are the magnitudes of the two vectors, and the A dot B is the dot product of the two vectors. Then we can actually calculate for the angle, which is theta, between what? Those two angles, right? So first of all, we need to find the magnitude of the two vectors, right? So the magnitude of A will give me the square root, right? So A is I'll have 2 squared plus 2 squared plus negative 1 squared. Alright, so this one gives me negative square root of 9, which is what? 3. So that's the magnitude of A. Then B, also finding its magnitude, gives me 6 squared plus minus 3 squared plus the 2 squared, right? So over here to end up with square root of 49, which gives me what? 7. Right. So since you have the magnitudes now, that means we can go ahead to actually calculate for A dot B. Right. So A dot B over here um, will give us a scalar since we are multiplying two vectors, right? So we actually have 2 multiplied by 6, right? 2 multiplied by 6 plus 2 multiplied by minus 3, then plus minus 1 multiplied by 2. Right, so this will result in 12 minus 6 minus 2, which gives me 4. Right, so that's the dot product for the two vectors, right? So if I have the dot product, which is 4, which is will be equal to 3, which is the magnitude, right? So the magnitude of A is 3, then that of B is 7. So 3 times 7, then cos theta. Right, so if I want to find cos theta, to be cos theta will be equal to 4 divided by what? 21, because 3 times 7 is 21. Then actually, I can actually calculate for my theta. So theta will be equal to the cos inverse of 4 over 21. So that gives me a theta of 79 degrees. Right? So this actually this is actually the angle for the two vectors, right? So we are still on um the mathematical review part of the fluid. Right, so let's move on to number 3. Right, so number 3, where we can see that they've actually asked us to calculate they've given us a vector, a velocity vector, and a force vector. Right, and they've actually asked us to estimate some things about them. So for the first one, they said if you calculate the magnitude. So for number 3, right, A, they said that we should calculate for the magnitude of V. Right, so the magnitude of V will be equal to the square root of 3 squared plus 4 squared plus minus 2 squared, right? Plus minus 2 squared, which will end up with 5.39 liters per second, right? So this gives me the magnitude of the velocity vector, which is very easy to do. Then for the B, they ask us to calculate for the dot product, right? Which is for the velocity vector. So I have 3I plus 4G minus 2K, and that's the velocity vector, dot the force vector, which is 2I minus 5G plus K, right? So since I have this one, it will be 3 times 2, right, plus 4 times minus 5, right, then plus minus 2 times 1, right? So I'll have 6, right, minus 20 minus 2, which gives me what? Minus 16, right? So this actually gives me the dot product between what? The two vectors, right? And the C, right, they ask us to evaluate the cross product for the two vectors and also evaluate the magnitude of the resulting cross product that we get the answer, right? So by here you can see that the V cross um, F. So using this formula, the determinant approach to actually calculate for it, we'll be having this, right? So we'll be having over here, right? So um I'll have the I multiplying by 4 minus 10, right? Then I have minus j. So using the conversion, right, I have um positive minus positive. So taking the first column, right? I'm taking the first column, taking the first row. So that gives me the 4 multiplying. So minus 5 times minus 5. That gives me the 10 over here. And over here, the conversion for the second column is minus. So minus j, that multiplies by 3 because 3 times 1 is 3. Then I'll have minus, then I'll have 2 multiplied by minus 2, which is minus 4. Right, then I'll have plus k, which is also gives me minus what 15 because 3 5 15. Then minus what 8, right? Over here 2 4 8, right? So over here I'll end up with over here 4 minus 10 is minus 6, so minus 6I. Then over here I'll be getting minus 7J. Then here I'll be getting minus 23K, right? So I have the cross product between what those two vectors, and they also ask us to calculate for the the magnitude. So they ask us to also calculate for the magnitude. So let's see how to also get the magnitude. So the magnitude, so the the magnitude of I have the magnitude of V cross F gives me the square root of um, minus 6 squared plus minus 7 squared plus minus 23 squared, right? So this gives me 24.78, right? So that's also the magnitude of that vector. So it becomes very easier, right? So let's just try the question 4, and let's see also how to evaluate some of the operations, right? So we have what we call the gradient of a scalar field, right, which will always land you in a vector. Then we have the divergence of a vector field, which will also land you in a scalar. You have what you call the Laplacian operator, right? So over here, question 4 actually give us a certain scalar and told us to find the gradient of the scalar at a certain point. So we have del S, right? So that's the gradient of the scalar, del S. So over here, the del operator is defined as del xi plus del yj plus del zk. Right, so this is a del operator multiplied by the scalar which the scalar over here is s squared y plus y z cube, right? So this is the operator I'm doing. So I'm finding the gradients on this vector field, right? So if I'm trying to do it over here, the meaning of this thing is that I'll be having I del x. I'll repeat that one on the scalar. So having this one, then plus j, I have del y also operates on that same scalar, right? Then plus to have the k, that also operates on the same one. So here we are doing partial derivatives, right? So partial differentiation. So differentiating x, right? So by I'm differentiating x. Right? So by here, if I'm differentiating the x, I'll actually get 2xyi, right? So over here, there's no term in x. Over here, there's no term in x. So that place becomes 0. Plus, for the y differentiation, I'll get s squared plus z cube, that's j. Then for the z1, z over here, there's no term in z over here, so it becomes 0. Then for the other side, I'll have 3y z squared k, right? So as I said, when you find gradients of a vector of a scalar field, it always end up in a vector. So putting in our points, which you have, so the point is 1, 2, 1. So x is 1, y is 2, right? So 1 squared, then this one is also 1, so 1 cube, j, then 3, y is 2, is 1, k. So over here I'll get 4i, then here I'll get what? I'll get 2j, then here I'll get what? 6k. Alright, so I've actually calculated for the the gradient of what's the scalar field, right? And right now for the part B, right? For the part B, we have so for the B part, we have the divergence. So they give us a vector field of xi plus the y squared j plus the zk, right? And it asks us to find the divergence of it, right? So trying to find the divergence, right? And this one will always also lead towards a scalar. Yeah, it will lead to a scalar. Right, so what you do here is that you have I x, right? So we have the xi, then plus, then you have the j del y, so you have the y squared j, then plus the, so you have the k, you have the del z, then we have zk. Right, so here these are differentiating with respect to x gives me 1, and I dot I is 1 2, so 1, then plus here I'll have what, 2, I'll have 2, so over here I'll have 2y, then over here to with respect to z I'll have 1, right? So yeah, I'll have 2 plus what, 2y, right? So that gives me the divergence of us the vector field. And the C part, they've asked me to also calculate for the Laplace of what, the scalar field. So the Laplace is just like the gradient, just that you do it twice. You get it? So you integrate twice. Right? So it's like so you'll be having del squared over del s squared. So s squared y plus the y z cube, then del squared del y squared s squared y plus y z cube, then I have l squared del z squared, then s squared y plus y z cube, right? So over here too, you end up with a scalar. So over here, the first one, so I'll do the first one. So if I do the first one, right, for x, I'll be getting 2xy. Then the next one will lead me to s squared plus z cube. Then the next one I'll have 3yz squared. Alright, so doing it again, over here I have 2y, Then over here it will be 0 because I don't have any term in y. Then over here it will be 6yz, right? Which ends up in 2y plus 6yz, right? So this will be for the Laplace of us, um the scalar field, right? Yes. Yes, so we have that one towards over there. Okay. So right now let's move to question 4. Where question 4 we are talking about a pitot tube, right? We are talking about a pitot tube. So over here, pitot tube um is one of the instruments that we use to measure the flow. Right, please you get it's one of the instruments we use to measure the flow, right? So the flow of a fluid. So for a pitot tube is easier, so it has its advantages and disadvantages. So fluids, all the flow meters that we're talking about a pitot tube. We have the venturimeter, we have the um, among others, right? So that's what I can talk about. So the question says that we have a pitot tube. So it's used to measure the airflow in a circular duct. So the circular duct over there, we have a diameter of 60 millimeters, which is actually 60 times 10 to the power minus 3 meters, right? Then it's flowing and the flowing air temperature. So they give us a temperature of 65.6 degrees Celsius. So you say that the pitot tube is placed at the center of the duct, right? So the manometer reading, right, that was given is 10.7 millimeters, right? So the manometer reading over there is 10.7 millimeters of water, and they give us a static measurement obtained at the pitot tube position is 205 millimeters, right? So we have the change in H, which is 10.7 millimeters, and that one is for 10.7 millimeters water, right? So this for the this for the pitot tube, right? So as we know, the pitot tube, we've connected a manometer across it so that we can be reading, and a manometer can be a water manometer or a mercury manometer. So we are using a water manometer over here. Right, so over here, and they give us another change in H, which is for the static pressure, right? Which is the 205 millimeters of water, right? So this is for the static pressure, right? So and they told us that we have a Pitot coefficient of 0.98, right? So 0.98. So the question said that we should calculate for the velocity at the center and the average velocity, right? So the velocity at the center, that's what we've been asked to calculate for, right? So over here, the question actually gave us the properties. So we have density, we have the viscosity at that temperature that they give us, right? So our work over here will be very easy for us when we actually find the static pressure in terms of Pascal. Right, so for the static pressure, right, we have change in H minus the rho of water minus the rho of the substance, right, times the gravity. So over here, the change in H over here the for the static pressure is 0.205. Right, that's in meters, right? You have to convert it to meters. And density of water is 1,000. Then the density at that temperature, which was given in the question, is 1.043. And then multiplied by gravity, which is 9.81. Right, so this actually gives us a static pressure of 209 Pascal. Right, so that's the static pressure in terms of what Pascal. Right, and if you want to actually calculate the pressure at point one, so when you see for the pitot tube, right, you can actually calculate for the pressure at point one, which gives us the atmospheric pressure plus the change in P, right? So that's the plus the static pressure. And we know atmospheric pressure is 101.3 times 10 to the power 3, which is 101.3 kilopascal plus 209. So this one gives me a P1 of 103.3 Right, 103.3 times 10 to the power 3 Pascal. Right. So this gives me what P1, but actually over here, since the pressure, the density that was given at 1 atm, but we've actually calculate for this pressure, which is not 1 atm, you have to actually calculate for the actual density of air at this pressure. Right, that's a correction that you have to make. So if you want to calculate for the actual density, we use the relation between density and pressure. So we will have the P1 divided by rho 1 being equal to PATM divided by the rho at what? The atmospheric, right? So over here, we want to actually calculate for the rho 1, right? So rho 1 will actually be equal to P1 multiplied by rho ATM divided by what? The PATM. So over here, we know that the P1 is actually 103.3 times 10 to the power 3, and PATM is 101.3 times 10 to the power 3. Then we know that the rule 1 should rule at ATM, which was given 1.043. Right, so this one leads us to a rule 1 of 1.064 kilogram per watt meter cube, right? So at this pressure, this is the density, the actual density we are coming to use, because from the question we can see that the density they gave us over here is 1.043, which is at as 1 atm, right? So you have to of course calculate for the density over here, right? So if we now have the actual density, that means that we can actually get what the actual what pressure. You get it? You can actually get the actual what pressure, right? So the actual, so we're calculating for P1 now. So P1 now will be equal to PATM plus the change in H, rho m minus what? Rho 1 times G. Because right now we have a new rule, so you have to recalculate for what? The pressure. So this one is 101.3 times 10 to the power 3 plus 0.205 to 1000 minus the new density 1.064 times 9.81. Right. So actually this whole thing gives me 103.3 times 10 to the power 3 Pascal. Right. So you can see that there is what the effect is what's negligible, because the P1 we calculated for and the new P1 are actually the same thing. So the effect was what's negligible. So that's the calculation for the static pressure. Right. So right now let's calculate the change in P for the Pitot, right? You see, we had a static pressure, then we had a manometer reading for also the Pitot tube too, right? So that one, the change in P becomes the change in H for the Pitot, right? Then density of water and G. So over here, for this one, it was 10.7, right? 10.7 millimeters. So 10.7 times 10 to the power minus 3. The density of water is 1000 minus the new density. That's what we are working with now, times 9.81. So this gives me 104.9 Pascal. Right. So since we have this for the P2, right? Since we have this one for the P2, that's what I'm coming to use to calculate for my velocity. So they say we want the velocity at the center. So the velocity at the center is the maximum velocity, right? So the maximum velocity or the velocity at the center gives us the CP. So the formula for the P2 tube to change in P divided by what? Root 1. And the CPU was given as 0.98 square root of 2 times 104.9, because we are using the change in pressure for the pitot tube, the 1.064, which gives me a Vmax of 13.76 meters per second, right? So that's the velocity at the center, right? That's the same thing as the Vmax, right? So we need to actually calculate for the Reynolds number to actually get our V average, right? That helps us to get the V average. So if I want to get my V average, I have to calculate my Reynolds number, which is the rho VD over mu, So the rho is still the 1.064 times 13.76 times the diameter, which is 0.6, right? Then the viscosity was given as 0.02 times 10 to the power minus 3, right? Because 1 centipoise is 10 to the power minus 3 watt Pascal second. That's the SI unit, right? So by here, this one gives me 439,220, which is approximately 4.4 times 10 to the power 5, right? And from a graph, right, you can see that there's a graph where the relationship, right, between the between Vmax, V average, I mean the ratio becomes 0.85. So at this Reynolds number, the ratio between these two is what, that value over there. So now V average becomes 0.85 multiplied by V max, right? So I have 0.85 multiplied by, so the V max over here is the 13.76. So that gives me a V average of 11.70 meter per second, right? So that, you see, is very, very simple to get the V average and the V max, right? And he asks us to also calculate for the volumetric flow rate, right? So since we have the volumetric flow rate, right, is equal to the V average, right? So the V average accounts for every other thing in the fluid, right? So you can't use the V max because it doesn't account for the velocities at the walls, right? So we use the V max to always calculate for um the volumetric flow rate, right? So we know V, right? V average is 11.70. Then you have to calculate for the area, which is the pi d squared on 4. So 11.70 times pi density diameter is 0.6 squared divided by 4. Right, and please always your area, you need to leave it in 4 decimal places. So the area is 0.2827 meter squared. Right, that's the area. So now the volumetric flow rate gives us 3.308 meter cube per second, right? And so that's the velocity, sorry, the volumetric flow rate at these conditions, right? So that's for a Pitot tube. Yeah, so all the flow meters, they all have their parameters and how we are supposed to work with them, right? How we are supposed to work with them. So let's move on to question 6. Question 6. So question number 6, we can actually see that we have a heavy fluid, right? So a heavy oil, right? So a heavy oil at 20 degrees Celsius having a density. So they give us a density, it's very obvious. The density is 900 kilogram per meter cube, and they give us a viscosity of what, 6 centipoise, which is 6 times 10 to the power minus 3 Pascal second, right? So the viscosity always needs to be in Pascal seconds, right? Then they say that it's flowing in a 4-inch schedule 40 steel pipe, right? That's how the pipe name is, right? They gave you the internal diameter to be 102.3 millimeters, which is 102.3 times 10 to the power minus 3 meters, right? And they say that if the flow rate is 1044 liters per minute, right? So we want to, so that's what is desired, right? To have a pressure drop reading on the manometer to be 93 kilopascal, right? So they want us to calculate the size of orifice, right? That should be used, right? So the size of orifice means that they actually want us to calculate d naught, right, which is the diameter of the orifice, right? So if you check your orifice meter, right, how an orifice is, you have an orifice, then you have where the thing is, the flow meter is connected to the pipe, where we have in the pipe diameter, and it's also being connected to what, a manometer, where we can readings can be taken, right? So over here, they actually want us to calculate for what, d naught, right? So since they want us to calculate for d naught, you have to, so the volumetric flow rate is 1044 liters per minute, right? which by conversion, right, to meters per second to be 1044 multiplied by 3 is the power 3, because 1 meter cube, right, is 1000 liters, right? So over here, then I'll have over 60 since I'm converting the minutes to seconds, right? So I'll have 0.0174 meter cube per second, right? So that's, you make sure everything is in the standard or the SI units before you continue your work, right? And they say that we should assume that the C naught is what, 0.61, right? So they want us to calculate for what, the D naught. So over here, we know that the formula for the orifice is actually that the orifice velocity is equal to the C naught divided by square root of 1 minus D naught over D1, which D1 is the pipe diameter, the power 4, then square root of 2 change in P divided by rho, right? So over here, we know C naught, we know change in P, we know rho, we know D1. So our task is to find what, D naught. But without D naught, we can't get what, V naught. So that's where our mass balance equation comes in, where we have V1 E1 being equal to V naught E naught, right? So you can actually calculate for V naught over here. So V naught is V1 E1 divided by what, E naught. And as you can see from here, you can see that V1 E1 is actually what, the volumetric flow rate, right? Because velocity times the area is volumetric flow rate, right? And here is E naught. So A naught is equal to what, pi D naught squared on 4. So putting that one inside, I'll have the V dot times 4 divided by the D naught squared pi. Right. So I know my V dot volumetric flow rate is 0.0174 multiplied by the 4 over there divided by, I don't know D naught, so D naught squared times pi. So V naught will now end up getting 0.0222 divided by D naught squared. Alright, so actually from this relationship, so let's say this one is equation 1, we can actually put equation 1 into this equation, the primary equation over here for the, so if you put it inside, I get 0.0222 divided by D naught squared, which, so C naught is 0.61 divided by square root of 1 minus D naught over, and I know D1, right? So D1 was giving us um 0.1023. So this to the power 4, this one also to the power 4, then square root of 2 multiplied by, so I was giving that one to be 93 kilopascal. So 93 times 10 to the power 3 divided by density, which is what, 900. Alright, so divided by density, which is 900. So over here, trying to solve, I will get so in the solving everything under the square root sign, right? Solving everything under that place and multiplying that thing by 0.61 and actually bringing it to the other side, right? So I'll be getting 2.532 times 10 to the power minus 3 divided by d naught squared is equal to 1 divided by square root of 1 minus, and over here 1 divided by 0.103 1023 to the power 4 actually gives me a value of um 9130.56. Then the d naught to the power 4 comes in, so that the equation will be much simplified to what, to solve, right? So since I get to that place, then I can actually do the um the inverse, right? So I actually have square root of 1 minus 9130.56 d naught to the power 4 will be equal to 3 94.94 d naught squared, right? So since I have this one, I can take square root of both sides to get 1 minus 9130.56 d naught to the power 4. So taking square root of that side, I'll be getting 394.94 squared times d naught to the power 4, because there's already squared over there, right? So making d naught to the power 4 the subject, I'll be having 165,108.2, right? So I actually have this one, right? So if I actually have this one, then d naught will be equal to the fourth root of 6.057 times 10 to the power minus 6. So I'll be getting 0.0496 watt meters, right? So that's d naught, right? So if I have d naught, yes. So the question wanted us to actually calculate for d naught. So I have d naught now, but you can actually verify if your this thing is actually correct, right? So if it's actually correct, then we need to calculate for the Reynolds number. Then we need to calculate for that the ratio between the orifice diameter and the pipe diameter, right? So you can see that the V naught now becomes 0.0222 divided by D naught squared, which gives us 0.0222. So D naught give us 0.0496 squared. So over here I'll be getting 9.02 meter per second, right? So that's actually the V naught I have now. So now Reynolds number will be rho Vd divided by mu, which is 900 multiply 9.02 times 0.0496 divided by 6 times 10 to the power minus 3. You will be having 6.7 times 10 to the power 4, right? So getting this Reynolds number, then I can actually calculate for this ratio 2 as 0.0496 over 0.1023. So the ratio gives me 0.4848. Alright, so we can see that since d naught over d1, right, is equal to 0.4848, which is actually less than 0.5, right, and the Reynolds number 2, which is 6.7 times 10 to the power 4, is also greater than 2 times 10 to the power 4, then, right, the assumed C naught, which is 0.61, is what? Is actually what? Valid, right? It's actually valid, and diameter, the orifice diameter should be, so we have 49.6 millimeters, which is approximately 50.0 millimeters, right? So this is actually for you to confirm whether the assumed orifice coefficient was actually correct, to get you the correct what size of what the orifice. Please, you get it? Yeah, yeah. So that would be for question 6. Okay. And since we are solving various problems regarding all fluid transport, right? You're solving a lot of equations. So right now we've covered from the mathematical review. Right, we've actually also covered the flow meters parts. Right, you actually covered the flow meters part. So let's actually also cover something on pumps, right? Let's cover something on pumps too. So over here we can see that we have a pump, right? So we are covering something on pumps too, because if we want to move a fluid from one point to another, we can use a pump to move the fluid to the other point, right? So over here, so if I have a pump, and you should know that for a pump, so let's say I have a pump. So let's say I have a pump. Right, so we have types of pumps too. Right, we have the centrifugal pump, we have the side channel pump, positive displacement pumps, right? They all have their functions, right? And the capacity they can work with. So if you have a pump, this side is what we call the suction side, and this side is what we call the discharge. Right. So over here, the pump actually takes the fluid, right, to this side. So this is a suction. Then it actually delivers it towards this side, right? So talking about pumps, you need to know what we call the Bernoulli's equation, right? So the Bernoulli's equation over here, right, is the overall mechanical energy balance equation, where we have in P1 over rho plus Z1G plus the V1 squared over 2, which will be equal to P2 over rho plus Z2G plus V2 squared over 2, right? So this relationship over here is what we call the Bernoulli's equation, right? And we also have the Bernoulli's equation where we want to account for pump work and friction, right? So if I want to account for pump work, on the right hand side over here, I'll be adding this one over here, which is the efficiency of the pump times the work of the pump, right? The work done by the pump. So over here, I'll add that one to this side. And since I'm accounting for the pump work and the friction, I also add what? The HF to this side, right? And accounting for all these things, if you want to calculate for the HF is we use the Darcy-Weisbach equation where we have the FD L over D V squared over 2. Alright, so we use the Darcy-Weisbach equation to calculate for the our HF. Right, if you want to actually get the HF, use the Darcy-Weisbach equation to get the HF. Yeah, so we can use that one to get the HF. Right over here, but since we want to use the Darcy-Weisbach equation, that means we need the FD over here. So if I want to get the FD, that's where I have to use the Moody chart, right? So the FD would depend on the Reynolds number and the what's relative roughness, right? The relative roughness, right? Where the relative roughness, right, will be equal to the absolute roughness divided by the diameter. So the absolute roughness will be given to you in the question. Then using the absolute roughness and the diameter, you can actually get the relative roughness. And from your Moody charts, you'll be seeing something like this, where we have the friction factor over here, which is the FD. We have the relative roughness here. They have the Reynolds number here. So let's say it's out 10 to the power 3, 10 to the power 4, 10 to the power 5, right? So when you get your Reynolds number, using the Reynolds number and your relative roughness, so you'll be seeing the relative roughness at this side. Right, so you're seeing some curves. And what you should know is that the first curve over here is for the smooth. Right, so when you have a smooth pipe, you don't need to get a relative roughness. You just trace your Reynolds number to the first curve, then you trace it to the FD to actually read for your friction factor. And the last curve over here is when we have the completely rough, right? Completely rough. That one is the last curve, right? So if you don't have any of them and you want to actually read the relative roughness, we read it over here. Then we move along the curve, right? If it's a curve, you move along the curve to actually meet your Reynolds number before you move straight to read what your friction factor. Yes, so that's basically everything that we need to know about the pump, right? And mostly you can ask you to calculate for the power of the pump, where in this relationship we use the mass flow rate multiplied by what the WP. So from this relationship, from the Bernoulli's equation accounting for friction loss and pump work, we actually calculate for this WP, which we multiply down by the mass flow rate to actually get the what the power, right, so of the pump, right? The power of the pump. Right? So that's it. So the power of the pump. So let's tackle the question 7. So if I've given an overview. So the question 7 is saying that a pump, right, draws a solution. The solution has a specific gravity of 1.84, so meaning that the density will be 1.84 times what 1000, right, which gives us 1840 kilogram per what meter cube. Did you get it? Then the diameter was given in the question over here as so we have two diameters. We have the 2 inch and we have the 3 inch, right? So the 2 inch, right, has a diameter of 52.50 millimeters. Then the 3 inch pipe has a diameter of um 77.92 millimeters. This is D1 and this is D2, right? And they gave us V3 to be 1 meter per second. So we have over here where the pump draws the solution from. So this is the suction side of the pump, right? So we have a pump like this. Then we have this. So we have the discharge side over here. So this is point 2. Then on the surface of the solution, we have point 1, right? Then it said that the surface to the discharge side is what 15 meters, right? So you have to sketch it so that you have an actual view of how the thing looks like, right? So we have this one, as you get it, and they say that the velocity in the suction, right? So here is the point 3, right, and here is point 4, right? Here is point 3. The velocity in the suction line is what 1 meter per second, right? And they give us an HF, right? So we accounted for an HF of 30 joule per kg, right? So they give us an HF of 30 joule per. That's the friction loss, right, in the piping system, right? And they give us the change in Z to be what the 15 meters, then efficiency to be what the 60%, right? So over here you write a Bernoulli's equation, right, between point 1 and point 2. So Bernoulli's equation between point 1 and point 2, right? So using Bernoulli's equation between point 1 and point 2, we know that P1 will be equal to P2, which is equal to 1 atm, because they all experience from the drawing, they all experience atmospheric pressure, and V1 is equal to 0 since the tank has a larger diameter than compared to what the pipe diameter. So the V1 becomes 0, right? And Z1 is also 0, because if Z1 is our reference point, from Z1, from point 1 to point 1 becomes what? There's no distance, so it becomes 0, right? So then, so since I have all these assumptions, I can write my Bernoulli's equation P1 over rho plus V1 squared over 2 plus Z1G, right? I'm accounting for pump work, so plus WP, then P2 over rho plus V2 squared over 2 plus Z2G plus HF, right? So over here I said the P1 is equal to P2, then V1 is 0, then the Z12 is 0. So on this hand side, right? On this hand side, it should be left with just this WP, which should be equal to V2 squared divided by 2 plus the Z2G plus what HF. Right, so you need to make some assumptions before what the Bernoulli's equation can work. Do you get it? Yeah, so over here, since I actually have this one, I have to calculate for V2, right, to actually put everything over here. So using my mass balance equation, now we having um A2 V2, which will be equal to um A1 V3, right? So over here, so I know that my V2 will be equal to A1 V3 over A2, which will be equal to D1 squared over D2 squared times V3. That one is much easier. So the diameter of one is 77.92 squared, and this one is 52.50 squared times 1, because V3 is 1. So V2 gives me 2.20 meter per second, right? So right now I have that one, so it becomes very easy for me to put inside my Bernoulli's equation and solve. Right, so I'll have PWP will be equal to, so I have the 15 times 9.81, that's the Z2 times G. Then V2 is 2.20 squared divided by 2. Then HF is 30. So over here, I'll be getting 179.57 joule per kilogram. Yes, that would be for this answer. So WP, we got 179.57 divided by 0.6, which is the 60%. So I have 299.3 joule per kilogram. Alright, that gives me WP. Okay, so I have WP, right, being equal to 299.3 joule per kilogram, right? So that's for the total work, right, by the pump, right? The total work by the pump. Then we can actually also write a Bernoulli's equation between point 3 and point 4. So as you can see from the diagram that I had over there, right, the diagram I actually had over there, you can see from the diagram that the suction side and the discharge side, right, they had the same elevation. So meaning that Z3 is equal to a Z4 because they were on the same elevation. When I do the pump like this, right? Point 3 was here, point 4 was here, right? So the same elevation. So Z3 is equal to Z4, right? Making that assumption, right? So it's negligible. So writing Bernoulli's equation between those 2 points. So I have change in P over rho plus V squared over 2 plus WP is equal to 0. Right, so since I'm writing a Bernoulli's equation for um between point 3 and point 4, right, I won't account for the friction losses over there. Since I'm not accounting for the friction losses over here, I'm accounting for just the WP, right? I mean the pump work over there because I'm taking a balance around just the pump, right? The mechanical balance. So over here, I'll be having the change in P will be equal to the rho. So I have V3 squared, V4 squared divided by 2 plus the efficiency times the WP. Right, so right now I have the density already. Right, then I have the V3, then I have V4 2, then over 2, and we know that the efficiency time the WP from the top over there gave us 179.97. 179. So from this one, I'll get a pressure of 327 what kilopascal. Right. So that gives me a pressure of 327 kilopascal because yeah. So the question said that we should calculate for what pressure must be developed, right? So we have the pressure now, and they're asking us to also calculate for the power. And so as I said from the top over there, that the power um is given by the mass flow rate times the WP, right? And so you know that mass flow rate is what? Rho VA, right? So the rho VA over here, we have 1500. The rho V over here is the V3, which is 1. Then we have to multiply by the area, which is A1, right? So A1 over here is D1 squared pi over 4, which is 77.92 times 10 to the power minus 3 squared times pi divided by 4. So A1 becomes 4 decimal places, 4.7686 times 10 to the power minus 3 meters squared. So the mass flow rate becomes 1040 times 1 times 4.7686 times 10 to the power minus 3. That gives me a mass flow rate of 8.77 kilogram per second. So now the power becomes 8.77 multiplied by the WP, which was 299.3, which gives me 2625 watts. right, which is approximately 2.7 kilowatts. Right, so the first one was the pressure which was developed. So right now we have the power developed by the pump, right? So yeah, we have that one. So basically that's it. So let's tackle question 8 and question 9. Okay, so let's now tackle the question 8, which is also similar to question 1. I mean question 7. The question is asks us to also determine the power needed to drive the pump, right? So that one is also power, right? Where we have the volumetric flow rate to be 2.3 meter cube per hour, right? Which in per second gives us 6.4 times 10 to the power minus 4 meter cube per second, right? That's the volumetric flow rate. Then you give us a change in Z to be 7.6 meters, right? Then we had a diameter of 50.80 millimeters, then a relative roughness, absolute roughness of 0.1 millimeter, right, from the question. So over here, from these two, you can actually calculate the relative roughness, which is this one divided by D, which is 0.21 over 50.80, which gives us 0.004, right? So I have this one. Then I have the length to be 119 meters, right? And they gave us an additional pressure loss, right, to be 2.44 meter of water, right? So that's, and they gave us a pressure loss of the fittings to be what, 300 pipe diameters, which is actually 300 times the pipe diameter, which is 50.80 times 10 to the power minus 3. So that gives us 15.24 meters, right? So we have all these things over here. So our first thing over there is to actually find our additional pressure loss in terms of what? In terms of an HF, in terms of joule per kg. Do you get it? So since the pressure loss, right, which is the frictional loss, is additional one, is the rho GH, right? If you want to find it in terms of what pressure, in terms of Pascal, so 1000 times 9.81. Since you are using water, so density is 1000, then the H is 2.44. So you have 23936 Pascal. Right, so our HF, so this Pascal in terms of the joule per kg, I just divide by the density. So I get 23936 divided by 1000. So that gives me 23.94 joule per watt kilogram. Right, so now I've actually converted down. The reason I'm doing this is because I want to actually get it into the Bernoulli's equation. So our HF in the Bernoulli's equation is actually in joule per watt kilogram. Right, the units over there, they are all in joule per kilogram. Right? So I need to also have the additional ones also in terms of joule per watt kilogram. Right. So per that, I need to get my HF also from the entire pipe length, right? So from that pipe length, I have to actually calculate for, I need my Daswell's back equation. So I need to get my Reynolds number, which is what, rho Vd over mu, which is 1000, which is the water, by, so the velocity, which is velocity is equal to the volumetric flow rate over area, so 6.4 times 10 to the power minus 4 divided by, so the area is 50.80 times 10 to the power minus 3 squared times pi divided by 4, because that's the area. So that gives me a velocity of 0.3 meter per second. So here it becomes 0.3 times the 50.80 times 10 to the power minus 3. And the viscosity of water is 1 centipoise, which is 1 times 10 to the power minus 3. So now the Reynolds number becomes 15240, which is approximately 1.5 times 10 to the power 4. Right, so that's the Reynolds number I have over there. So using this Reynolds number and a relative roughness which we got 0.004 from the relative roughness, right? Then using the Moody charts, we get a friction factor of 0.034. Right, so getting a friction factor of 0.034, you have an HF using the Dasrius-Bach equation, we have an L plus L equivalent, right? Since we had everything over there, then we have V squared on 2. So the FD is 0.034, then the L was 190 plus 15.24, that's the equivalent length, over the diameter, then 0.3 squared on 2, right, which is the velocity. So that gives me 5.7 joule per kilogram, right? So you see that they gave us an additional pressure losses, right? So we add the 23.9 to the 5.7, then we get 29.6 joule per kg, right? So this gives us the total frictional losses, right? So that you can put that one inside the Bernoulli's equation. That's what we want to do. Over here, let's write the Bernoulli's equation. So writing the Bernoulli's equation, right? So P1 over rho plus Z1G plus V1 squared over 2, right? Plus the P, WP is equal to P2 over rho plus Z2G plus V2 squared over 2 plus the total of the frictional losses. And you can see that at point 1 and point 2, the whole experience was atmospheric pressure. So P1 is equal to P2 and V1 is 0. V1 is equal to V2. They are the same thing, right? We got the same pipeline, so the velocity also becomes 0, right? So over there, then so from here, if I make WP the subject, I get change in ZG plus the total summation of HF divided by my efficiency. So this one becomes 7.6 times 9.81, then plus 29.6 divided by 0.66, which was the efficiency. So WP becomes 104.156 divided by 0.68, which is 153.2 joule per kilogram. And so that's the WP. So now you can find the power. So the power is the mass flow rate times the work, right? So the mass flow rate becomes 0.64, then the work is 153.2, which gives us 98 watts, right? So some people are wondering where the mass fluid came from. So as I said, from the overall mass balance equation, right? And you know that velocity times area is the volumetric fluid, and the density was 1000. Volumetric fluid was 6.4 times 10 to the power minus 4. So that gives us a mass flow rate of 0.6 kilogram per second, right? So that's where this thing came from for us to get that power. Right? So it's very easy to do, right? And question 9 also follows the same approach, right? Question 9 also follows the same approach, where we use that one to actually solve, right? The only thing added to question 9 is the NPSH, right? Is the NPSH. So let me use this example to illustrate NPSH. So you know that the NPSH, the net positive suction head, right? So we have the pressure head at the source. So at the source, which is P1 over rho g, that's the pressure head at the source. Plus over here is either a suction head or a suction lift. Right? This is a suction head is positive. If it's a suction lift, here becomes negative. Then minus the friction head, right? Is HF over G. Then minus the vapor pressure head. So that's NPSH, right? And one thing you should know is that the NPSH you calculate is the NPSH which is available, right? So NPSH available. So if the NPSH available is less than the NPSH required, which is um, specified by the manufacturer, meaning that cavitation will occur. You get it? So always you make sure the NPSH available is greater than your NPSH required. That means that no cavitation will occur in the pump, right? So per this one, the pressure at the source, right? The pressure at the source was 1 atm, which is 101.3 times 10 to the power 3, right, in Pascal. Then the density 1000, then 9.81, right? Then the change in Z was given as 7.6, right? Then HF, right? So we had let's assume we are using the total at HF, right? So the total HF was 29.6 divided by 9.81. Then let's assume the vapor pressure in this question is the 28.9. So 28.9 times 10 to the power 3 over 1000 times 9.81, right? So this actually gives me the NPSH, which is the net successive net positive suction what head. Did you get it? So let's compute the value for so computing the value for this one. Now have it's one, then plus 7 point. So let's assume the elevation there is a suction head, right? So over 29.6 divided by 9.81, then minus 28.9, right? Point 9, then I have 1000 times 9.81 times 10 to the power 3, right? So I had an NPSH of 10.67 meters, right? So that's it's measured in meters, right? So this is the NPSH available. So let's say the required is if the required is, let's say, 7 meters, right? Meaning that your available is greater than the required. So meaning that um there's no cavitation, which is okay. But if this one becomes less than your required, that means absolutely cavitation, okay. Okay, so question 9, that's the only thing that came in question 9, the NPSH, right? So yeah, thank you.